G'day team, welcome back to another video. Today we're going to start looking at the principle of mathematical induction. And now what that is a method of proving mathematical statements. And today we're going to sort of look at the most basic one, which is a series. So a series is a bunch of numbers added together. So if I have 4 plus 8 plus 12 plus all the way up to any multiple of 4, so this is 4 times 1, 4 times 2. So if I've got 4 times n, we can say that that sum is equal to 2n times by n plus 1 for all n greater than or equal to 1. Now, a mathematical induction proof has a few key features. So it has my n sort of statement, so my general statement in terms of n. It has my base case, so I choose n equals 1 or n equals 2 depending on my condition on n here. And then I also have to show that I've got a general case pk and then I've got the next case. So basically we're proving if the first case is true and any case is true plus the next term is true as well, then we can say that the whole series is true or the proof is true as well. So let's have a look at a really basic example here. So my P of n statement is actually just my proving statement that I've written there. So 4 plus 8 plus 12 plus ... all the way up to 4n. And that is equal to 2 times by n plus 1. So that is my P of n statement. Now let's prove P of 1. Now on the left hand side of this equal sign, I'm going to substitute 1 in for n here. So I've just got 4 times by 1, which is 4. On the right hand side, I'm going to do the same thing. Substitute 1 in for n. That means I've got 2 times by 1, and then I've got 1 plus 1. So I've actually got 2 times 2, which is 4. And that means P1 is true because the left hand side equals the right hand side there. Okay. Base cases are usually pretty easy to prove. Obviously, the trickier bit comes in when we're proving a general case. So just like we did with n equals 1, we're going to substitute n equals k into my P of n statement. But I'm going to write the whole statement out. So it's going to be 4 plus 8 plus 12 plus ... plus 4k. So I've substituted k in for n, which is equal to 2k k plus 1. Okay, so all the n's have now just become k. And we want to assume that this is true. And what we're going to do, we're going to use this fact in our next part. So we're going to assume pk is true. And now we're going to write out p of k plus 1. And that is just the next term along in my series. So I've got now 4 plus 8 plus 12 plus ... plus 4k plus 4k plus 1. Now, I've substituted in k plus 1 for n, so I have to do that on the right-hand side as well. I've got 2k plus 1, and then in brackets, k plus 1 plus 1. Okay, so you can see this k has become k plus 1, and this k has also become k plus 1. Now, you may also notice we can simplify in there, so let's do that now. So I've got k plus 2. All right, so we are going to actually prove this now, and we're going to sort of look at the left-hand side and see if we can get it to match this right-hand side. Now, if I look in brackets and I sort of bracket off this little section here, we notice that that bit there is actually pk. Okay, so it's the left-hand side of pk up here. So what we can do, we can actually substitute all of this stuff here for the right-hand side of pk because we've said that it's equal. Okay, so we can actually write the left-hand side as 2k k plus 1 plus 4 times k plus 1. Okay, and we want to just now start working this through so that we get this part here. So let's expand this out. I've got 2k squared plus 2k plus 4k plus 4. Okay, so let's keep working this out. I've got 2k squared plus 6k plus 4. Now, this looks like a quadratic, and I've got a common factor of 2, so let's pull that out the front. So then I'm left with k squared plus 3k plus 2. And now we can use sums and products for this quadratic. I've got a k, I've got plus 2, and then I've got k plus 1. Now, they are a slightly different order to my right-hand side up here, but they are the same because they're just multiplied, so that is equal to the right-hand side, which is our check. So that means p of k plus 1 is true, given pk is true. Okay, so since p1 is true, okay, and pk plus 1 is true whenever pk is true, so we use pk is true in our pk plus 1 proof, then p of n is true for all n greater than or equal to 1 by the principle of mathematical induction. Now, pretty much all series mathematical induction questions will involve this step of replacing this section here with the right side of pk, so you can utilize that as well. Hopefully this has explained PMI in a nutshell. This is obviously very structured, so often you won't be given these, so you have to create P of n, P of 1, left-hand side, right-hand side, etc. All right, we'll see you guys in the next video. See you then.